Hello everybody, welcome to another video lesson. Today we're going over circular and periodic functions, mostly periodic functions today. We're going to be able to find values of our trigonometric functions with the unit circle. We're going to take another look at that today. And then we're going to use properties of our periodic functions in order to evaluate some trig functions. So let's hop into it with our unit circle. Now hopefully you guys have seen this before. Oh, we are missing a point here. Let's see, we're missing 1, 0. This is our unit circle. Now, any unit circle is just a circle with a radius of 1 unit. That's why it's called the unit circle. Now, why this is important is because if I take a look at some angle, just take a look at, as an example of angle, 30 degrees. Okay, if I were to go ahead and create a triangle, a right triangle, trigonometry, what's a bit of a pattern we're seeing here, right? So let's take a look at this triangle here with 30 degrees. Now, my x value, or my horizontal value here, is going to be √3/3 and 1/2. At least that's what our unit circle says right here, right? And we know that our radius is 1 all the way around this circle, right? So my hypotenuse for this triangle is then going to be 1. Okay, so if I take the cosine then of 30 degrees. Cosine is adjacent over hypotenuse, remembering our SOHCAHTOA. Our adjacent is √3/2, and my hypotenuse is now 1. Okay, so that gives me a cosine of 30 degrees equaling √3/2. So the nice thing about this is any x value, okay, if I have a coordinate on my unit circle, xy, that's really cosine theta sine theta. Try to squeeze that in there. Okay, so my cosine and my sine are now the xy values of my coordinates, which is really, really helpful. So then let's see if we look at it again, sine theta, just to kind of verify this. Hopefully it's 1/2, and it should be, right? If it's opposite, which is 1/2 over adjacent, sorry, this should be not adjacent, this should be hypotenuse, right? For sine. So that's going to be 1/2 over 1, which is just 1/2. Okay, so that checks out there. So why this is even more important now is if I go ahead and extend this triangle, okay, I keep my angle here of 30 degrees, but I'm extending this triangle to something much larger. Okay, so now it's kind of outside of my unit circle, right? It's got a hypotenuse larger than 1. So this is somewhere out here, right? This relationship, because this is simply a relationship of the legs of my triangle, since the proportions of these legs aren't changing at all, guys, if I go ahead and look at the cosine of 30 degrees of this larger triangle, well, it still just equals √3/2. Okay, so these relationships extend to triangles of any size as long as these angles are the same. All right, so that is how this is even more helpful, because this really works well outside of the unit circle, but I still have the same values when I'm looking at sines and cosines and all my trig functions. Okay, now let's take a look at our periodic functions. A periodic function is just a function with function values that repeat over certain intervals. Now, the interval length, we're going to call the period, and we'll take a look at that here in a second. But let's take a look at some examples. And the first one, we'll go ahead and graph a trigonometric function, let's say sine of theta. Okay, f of x equals, I guess that should be f of theta equals sine theta. F of theta equals sine theta. So if I were to graph that then, notice how starting at from -2 pi all the way to 2 pi. Now what happens after that? Okay, I have this point here and this point here. Okay, do we see how from 0 then to 2 pi, it's the exact same shape, right? It's the same function values. They start to repeat each other over these intervals. So keep an eye out for that, especially graphically. That's a very easy way to tell what a period is. All right, so my general example then, if I were to just craft some random lines here, my period again is the length, the horizontal length that it takes to complete one cycle or one pattern of my function. So one complete pattern then for this example here on the right, we could see they start to repeat, our values start to repeat when they reach 2 again, right? Okay, so every time my function hits a value of 2, I'm starting to repeat itself. Okay, so if I were to say, okay, this is from -4 to -1, then I would say I have a period length of 3 units. So that is our period and our periodic function. That's why they're called periodic functions, because they repeat over an interval, which is called our period. So let's go ahead then and get into some examples then. Our unit circle, looking at cosine and sine. Okay, let's see. We have the terminal side of theta in standard position intersecting the unit circle at this point here. Find cosine and sine. So if I go ahead and bring up my unit circle, notice I don't have coordinates 3/5, -4/5, right? Okay, but that's okay because again, like I said, on any for the unit circle, any coordinates that we have, we can express that as the x coordinate being cosine and the y coordinate being sine. So in this instance, my x value here, this would be our cosine, and my y value would just be the sine. So cosine theta would be 3/5, and sine theta would be -4/5. Simple as that. All right, let's take a look at an example of determining the period of a function. Okay, we got a function here, we've got a graph. Now we need to just see where our function values start to repeat themselves, okay? Now be careful because you might take a look and say, well, it starts at 0 here, and then it goes, and then it hits 0 again here. So maybe this is my period length from 0 to 4 pi. But be careful though, because this whole bowl right here, this bowl shape on my graph, okay, that hasn't repeated anything yet, right? Okay, I've got the top half of my curve and then the bottom half of my curve, and then we hit 0 again, and then we start repeating from there. Okay, so just because I hit, say, the x-axis or some value twice doesn't quite mean I've fully gone a period length. Okay, I need to wait until the whole iteration starts over again. Okay, the whole curve would have to start over. So in this instance, okay, from 0 to 8 pi is where we start to see some similarities, right? And we start to see some repeating function values. Okay, so again, from 8 pi to 16 pi, so we go another 8 pi, and then from 16 pi to 24 pi, as you can see, guys, we have 3 periods here. Okay, this being the first one, and then we start repeating in the second one, and then again we start repeating in the third one. Now, it doesn't matter. I don't have to be crossing the x-axis for a period. Okay, we can take a look at these maximum values right here. Okay, this first one I've got, I'm seeing this at 2 pi. We're hitting this maximum value, and then we go all the way to 10 pi, and I hit that maximum value again. So you can see now, again, I've got a period of 8 pi, and I just found it in a little bit of a different way. I'm looking at a different point on the graph to wait to where that starts to repeat. Okay, so then again, I go down my bowl and back up, and that takes 8 pi to do that, so I get to 18 pi there. And then again, one more time, we get to 26 pi, and that would be, again, 3 period lengths here on my graph. But for this one, both of these are the same, which they should be, and we have a period length of 8 pi. That's where we start seeing our repeating function values on our intervals. Alrighty, another example. Here we have a cyclist pedaling a bike at a rate of 1 revolution per second. The height of the pedal varies periodically as a function of time. Now you can see down here we have a figure for a pedal at 1/2 revolution per second. Okay, so this is a 1/2 revolution per second. And this is just giving us the height of the pedal at certain time stamps. So this is a 1/2 revolution per second. So the context of example 3 is 1 revolution per second. So that is actually going to be faster than, the example that we have here for our figure. But we need to do a couple things here. We want to make a table showing the height of a bicycle pedal at times, and gives us certain times. It's every 1/2 second from 0 to 3 seconds. And then we want to identify the period and graph the function. Okay. So all we need to do, knowing that this is 1 revolution per second, right? If it starts off up here at 18 inches, where would it be when it was at a half second? Well, I know it's going to be back at 18 inches, right, at 1 second. So where would it be at a half second? It'd be halfway through that revolution. So that would then be here at 4 inches of height, okay? So the start of every second at 0, 1, 2, and 3, we're going to be at a height of 18. And at every half second, we're going to be down here at the bottom at a height of 4 inches, all right? So we can go ahead and start graphing this. And we're going to just plot these points out that we have. Okay, so I've got 0, 18, 0.5 and 4, 118, 218, 318, and then every half second we are at a height of 4. Okay, so if I were to go ahead and draw a smooth curve going through these lines, it would look something like this. Okay, and we can clearly see then, even if we kind of saw this before, where we start seeing these repeating values, well, it's every second, right? Which makes sense because it's 1 revolution per second. So that makes sense that it starts repeating height values after each second has gone by. Okay, so our period length here would be 1 second. All right, last example, we're going to find the exact value of a couple of trig functions using the characteristics of periodic functions. Okay, understanding that cosine and sine are going to be periodic, we can go ahead and use that to our advantage when we're given a cosine, or when we're asked to find, say, the cosine of a value that is not in our unit circle, right? Negative 3 pi over 4, that's not in our unit circle. However, I know that if I find an angle, a coterminal angle to 3 pi, negative 3 pi over 4, yeah, then I will effectively start to repeat my function values, okay, because of that identity of periodic function. So let's go ahead and find a angle coterminal with negative 3 pi over 4. And to do that, all I need to do is add 2 pi. It's that simple. Okay, so if I add 2 pi, that's going to be just like adding 8 pi over 4. Okay, so if I add 8 pi over 4 with negative 3 pi over 4, that gives me a positive 5 pi over 4, which is great because that is on my unit circle, right? Okay, so what we're saying here is that the cosine of negative 3 pi over 4 is equal to the cosine of 5 pi over 4. And that is because it has these repeating function values for cosine, because it is a periodic function. So we can then go ahead and take a look at our unit circle, and I can identify our angle of 5 pi over 4, okay, or 225 degrees, but we're working in radians here, so 5 pi over 4. And we have coordinates of negative root 2 over 2 and negative root 2 over 2. Okay, so I know that the x coordinate for this one is going to be what we're looking for cosine, but they are the same for both x and y. So cosine of negative 3 pi over 4 is going to be negative root 2 over 2. So you guys pause the video and use this same process to see if you can find the sine of 420 degrees. Okay, here's the process that I took. I subtracted 360 and then found that angle of 60 degrees and found that sine of 420 was equal to root 3 over 2. Okay, hopefully that's what you got. But that's all I have for you guys for this video. Good luck with your practice.